Open table. And you know the rest, Lamppost Group? Carbon 5, EPB, CoLab, Society of Work. Yeah, I'm not making you tweet today. I just felt like it. So I did it. CHADEV, ball out. Social media, you know where we're at. Hit us up on Instagram. Or, when's the last time you did one of the Humans of CHADEV?
You could, if you wanted to tweet, say something about Slack giving us their Slack for nonprofits.
Ooh, yeah, that's right. That's right. Holler at Slack today.
HQ. Don't say they sponsored us because they're sensitive about that, but thank them for making their nonprofit program available for us.
Yes, they gave us, now we all have unlimited history. So all of the embarrassing things that any of us said on there now in the public channels, you can go back and search. Normally it's what, $8 a person, I think, or seven a person, so it'd be $700 a month we're saving. So, you know.
$6,000 a year.
Yeah. There we go. So shout out to Slack HQ. Okay. Yes, meetups. Check them out. Man, so many meetups. Just at the Art Dev meetup last night, that was a lot of fun. We've got the Carbon 5 Hack Night next week, which has become something of an unofficial Elixir meetup as well. So holla. CHADEV survey. Jared, why don't you come up and give us a word about the CHADEV survey? Hold on, I'm gonna pass the mic to you. You get a mic, it's official now.
All right. Well, earlier today, I was described as the CHADEV survey guy. So that's my name, CHADEV survey guy. All right, so the CHADEV survey is about kind of context for your career and transparency for the community. So there's a survey, you can go to that URL and check it out. We'll ask you some sensitive and non-sensitive information. The idea is not to find out who you are. The idea is to tell us about you so we can tell you about each other. It's kind of like Glassdoor for our community. I know it's kind of confusing, right? You know? Let's see, where was I? I lost my train of thought here. Yes, but it's not like for your employer to know how they can like lord it over you. It's for you to kind of empower yourself to know if you're doing a great job with your career or if you can kind of work harder, do better, gain some new skills, and improve your piece of the pie that you have here in the community. So check it out. We will not try to figure out who you are. I think I'm the only one that's going to look at the full data set. I'm going to create a report and release that to you guys so you can see all the cool data points that hopefully come out of this data set. Currently I have 23 people that have done this, and Andrew's saying like 80 to 90 would be ideal. So if you haven't filled it out yet, do it. And,
how many questions is it?
I don't know. I just kind of made that's a good question.
It's not that many.
It's like 15 or something.
Yeah, it's like 15 questions.
And what's like the most sensitive pieces of information you're going to want from people, just to make
Probably your salary.
Okay.
And maybe years of experience.
All right.
Depending. If you're like the only person that has 100 years of experience in the community, you'll kind of figure out who you are, but you know. Anyhow.
Oh. All right.
Where's Richard? I love him. He taught me.
Sweet. So yeah, definitely go check that out. Pass it around to your friends and coworkers here in Chattanooga so we can all get a good idea of what's going on here. Wow. We've mentioned it, Slack. You know where it's at. We got the unlimited history now. Go dig up all of those embarrassing things that you remember that you couldn't find before, and now you can. Whew, we're on Freenode as well. Get on it, and GitHub. Job board, it's a thing, it's happening, there's jobs there. Go look for them, submit them. Job time, second Thursday of every month, is it? No,
Yeah,
what is?
That's correct, but it's not.
Yeah, we're not the second Thursday, we're well past that. I don't know, we probably need to check in about that soon, about how you guys are feeling about that. These slides, of course, you can get them here. And without further ado, the Internet 2.0, Andrew, Ace Drew, the Rodgers.
Twice.
Oh yeah. Well, I wanted to make sure that you got that. That's why that's there. So, The handoff.
The handoff. Super subtle.
Seamless transition.
All right, so I really did this whole presentation as an opportunity for the community to rack up an achievement, and that achievement is sitting through an 83-slide presentation. So that's why I'm a little nervous. I may just use the arrow keys because they go fast. So I'm Andrew Rodgers. I'm on Twitter at Astrew, at Instagram AstrewCha. See, this is not the game I wanted to play. Not at all. All right, there we go. Oh, the wrong way. See, this is. Back to the beginning. All right, so I'm a technologist. What is a technologist? That's a good question. This is the definition I use. It's very broad, and I work on a very broad array of things. I work for a few organizations. I work with the Enterprise Center as their technologist in residence. I work with CoLab as their technologist in residence, and I am a control systems and network infrastructure commissioning engineer for Compass Commissioning and Design, which is way too long of a title. My passion, though, is really using technology for social good, and I get to do that both with CoLab and with the Enterprise Center. And I'm here today to talk about the internet, what it is, what it can be, and kind of where it got started to better understand what could be looked at as problems with the internet. So try to be sensitive. So this is an old thing. It's been around a while, right? Our DARPANET, 1969, you guys know that story. And this is the OSI model, and it's also really old. And if you don't believe me, just look at that graphic. They've been explaining this so long that even the graphics are really dated. And I like to think of the OSI model. It gets described as different processes, and I like to think of it more of layers of encapsulation around the data you care about, your application's actual thing that you're doing on the internet. And turns out that layers cost money. You have to open the layers, you have to close them back up, all that. And the reason why we ended up with the OSI model was partly due to the organic growth of the internet. And organic is great. We wouldn't have the internet if it wasn't for this organic growth. But there are some problems. So the internet and networks in general, when you have two devices, they're pretty simple, right? You can have a computer, a switch, you tell the computers about each other, they know about each other, they can send data to each other. Very simple stuff. But as the internet grew, you had a couple computers at one university talking to each other, then you had computers at two different universities talking to each other, then you added some more universities, then you had statewide academic networks that were connected across state lines. Then you keep adding more of those, you start adding other countries to the mix, ad infinitum. You start interconnecting those, so rather than kind of going through any central, you can reach any other point of the network from another point of the network, and then you double the size of that. And then you double the size of that. And it becomes really, really, really hard to reason about where your data is going and how it's getting there and why it's taking the path it's taking. So organic is great until you get to a certain point and it becomes very complex. This is a small snapshot of a subsection of today's internet. And if you can make sense of that, then you got better eyesight than I do. Anyway, it's just to illustrate just how complex it is. The colors mean something, and it's not important. So the internet as it exists today is a distributed system. I think if you do anything in computer science, you know that distributed systems a lot of times are hard, and you have to make a lot of trade-offs to make them work. And one of the trade-offs that the internet makes is determinism. So when you send data across the internet, you really don't know what path your data is going to take, and you don't know how long it's going to take to get there. Depending on the protocols you use, you can get some guarantee that you'll know if it doesn't get there, but really that's all external layers above the lowermost infrastructure. So distributed is good, resiliency is good. The beauty of that is if any one of those nodes in that diagram dies, the data is just going to find a different path. All the nodes around it are going to route the trade. So that's a good thing. It's decentralized. No one person, no one entity has control over the entire thing to some degree. In the US has most of the major infrastructure. That story is kind of true, but anyway, they're trying to work on that right now, actually, making it non-US. The bad for this sort of thing is that it's decentralized. You don't have control over the entire network. You don't know how the network's going to react to what you're doing to it. You really just have to kind of try things and see, because it's so large and so complex that you really, you could simulate it, but the time involved in simulating it is greater than the time in just trying to use it. And the determinism, so not knowing, A, where your data is going, so you don't know who along the path might be looking at your data that you don't want looking at your data, and you don't know how long it's going to take to get there, which becomes really problematic with things like video, where if a part of the video frame gets to the endpoint after that frame has already been displayed, it does nobody any good. So video is one of those things that's really test the capabilities of current packet switch networks. It's really on the edge. And efficiency. So when you have all these layers of encapsulation, it's like sending a house via UPS, packaging the entire house up in boxes. You have to put foam around it. You have to put an address on it so people along the way know where it's going. It's a lot of work. Cutting a house into box-size parcels to ship on UPS is a lot of work. So you lose some efficiency there. And again, just the sheer complexity of all these routers making their own autonomous decisions about where traffic flow should go in the core network. To just illustrate how complex it is and how that's a cost to the system as a whole, IPv4 has run out of addresses again, supposedly this week. This has happened 4 or 5 times, and when it happened the first time, they released a standard called, oh look, I swiped it. They released a standard called IPv6. That was 10 years ago, at least-ish, and we still don't have IPv6 on most commodity internet connections because it takes that long to upgrade and replace all this autonomous infrastructure throughout the system to support a new standard. So it becomes, when everyone is autonomous and has control of their own stuff, it becomes really hard to coordinate things like a standards upgrade to support new capabilities. So I'm going to talk today a little bit about the next internet, what it might look like, how some research networks that exist today are influencing that, and some of the problems with those actually. So GENI, which is the Global Environment for Network Innovation, is a research academic network. It was kind of formulated in 2005 and funded in 2008 by the NSF. And it took a bunch of links that already existed between, with $12 million, by the way, and 29 partners. So those 29 partners were research institutions and national labs that already had high-speed links set up between their locations. And it took those and turned them into a cohesive system that would act as a test bed for research and around the actual core of what the internet is and what it should be and different protocols and that sort of thing in a very isolated sandbox environment where the researchers didn't screw up everything for everyone else. So that has been going on for the last 7 years or so. It's expanded, and one of the things, and this of course allowing collaboration on these, because setting up a network lab at one university doesn't do much good for everyone else that's working on the same problem if you can't really connect them, because the only thing that exists between there is normal infrastructure. And so GENI gives a lot of flexibility for this. It is mostly used by academia. So fast forward 2015, Chattanooga gets GENI at UTC, but there's a core difference in how it's implemented here, in that because of EPB's network and because of a special arrangement with the NSF, UTC, EPB, the 60 plus partners that now make up GENI from the 30 that it started with, they're allowing us to do community outreach. So we can take this network that's connected to 60 plus research universities across the country and take it all the way out to the edge of EPB's network. So whether that's a business that might be collaborating with a research team, or education system where we're trying some next generation education projects. US Ignite last week got funded with $6 million to take what we're doing in Chattanooga and expand that to 14 other cities, for a total of 15 cities that will have the GENI network embedded in them and accessible for civic and education-oriented programs. So it turns these cities into living labs where taking it from a research, something that you're just playing with in a lab, to, okay, how does this impact an everyday user of the internet. So I'm going to stop for a second and talk about Internet 2, and specifically AL2S, their Advanced Layer 2 service. So Internet 2 was a backbone research / academic focused, education focused network that already existed when Genie was formed. But really all it was a high-speed packet switch network. It had a big backbone at the time, 10 gig links around the country. Now it's a whole 100 gig backbone. And recently, I think last year, they switched their 100 gig backbone from being a packet switch network to being this advanced layer 2 service, which means that any data that flows on that network is treated as a dedicated stream of bandwidth that is from one point to another point. And so they actually offer packet switch services on top of that platform, but it's virtualized, which is really cool. This is what that network looks like. These are all 100 gig pipes. You see we have 100 gig coming through Chattanooga, really, but we're actually on a little 10 gig stub back down to Atlanta is how we get connected to this. Genie is actually being in the process of being virtualized and put onto the Internet 2 network as well. And what AL2S does, and this is technology that was developed on Genie, and then AL2S being kind of the first prototypical production network that's using it, is this point-to-point, completely layer 2, transparent linkage. So you get full orchestration on your network. There's one single control system that defines the state of the entire network. So when you think about, as developers, you think about maintaining state and it getting moved around a lot. That's one of the problems with packet switch networks is your state is completely distributed and you really don't have any way of knowing what the state is in any of the nodes without trying to send traffic through them and seeing what happens. And so with orchestration, you get the ability to know exactly what the state is. And so if I want to send data across the country, I can do that and I can say I need 100 megs of bandwidth and I need it for the next 4 hours, and it will provision a link from me to wherever I'm going with that much bandwidth, guaranteed pass through. There's no routing, there's no packet switching that happens on that. It looks like my device is plugged into the other device. So it's centrally managed. It's deterministic because I can define where the path is going. I know exactly how much time it's going to get there, and all of my data is taking the same path. And the data path is defined before transmit. I can actually know how and where the data is moving before I ever send anything on the network. Reliability is different, right? So with resiliency in a switch network, if we lose a device, we just route around it. With this, you kind of get a switch on your reliability on what level you want. So if it's not real critical data, or it doesn't matter if I have to restart sending the data, if lives aren't at risk, I can just provision the link and it'll work. However, if it's something that's really important, say data about a power grid or something like that we really care about, the timing and the fact that it gets there, I can actually provision redundant paths. And so it will take the two paths, it will time out the one that's the longest, and my data will always arrive at the end destination at the longest time. And so if it gets the shortest path first, it just holds the data until the longest path gets there. If the longest path doesn't get there, it just pushes the data on at the timing of the longest path. So I get full redundant data transmission just on the fly. Bandwidth's reserved for each data flow, so if you say I need 100 megs and there's not 100 megs on that pipe, it just doesn't give it to you, as opposed to being oversubscribed and having to deal with packets being dropped or queues loading up and you losing your determinism. So resiliency is a lot different. It's programmed in. It is not distributed. It is not autonomous. Covered the dynamic redundancy. Security is interesting. So we move from a model where we say we are blacklisting security to a whitelisting security. So the only data that can come into you is what you allow to be provisioned by the central system. And vice versa, data you send is only going to reach the endpoints that you care about, that you tell it to send to. This brings up trust. So a lot of people, I gave this talk without these slides, and the first question was, well, what about the NSA? And it's like, well, the NSA wants to know what you're sending on a network. They can do that. So the problem, though, is now even with things like Tor, they're finding out, Tor is designed to give you, you can encrypt data, and that's fine, and encryption works pretty well, but knowing who's talking to who is what Tor is supposed to solve. And there's been some really critical flaws in Tor found recently where it kind of falls apart, and they're actually able to determine who's talking to who. In this case, the one entity, the central system, knows who is talking to who for everyone, and you just kind of give that up by default. So you have to trust that one entity. If you don't trust it, then that's fine, but on the regular networks, there's a million entities between you and where you're going, and you have to have some amount of trust in all of them at some level that they're doing what you think they should do. Covered latency as well. The really interesting thing is it actually cuts down on latency more than you would think because there is no decision tree being made in the network hardware. There is no, oh, this packet's addressed for here, I need to send it here. It says packets coming in, or not even packets, frames coming in on this pipe, go out that pipe, and it switches that in, and it's in line. And they're even working on ways to do this optically so it never hits copper, which is really fascinating. So you get really low latency. Efficient, I don't have to, my data doesn't have to be encapsulated and packaged and have addresses on it. I can just push my data down the pipe to the application that's expecting it. Data and control are completely separate. So again, no addressing, no kind of layers of encapsulation, but there's a separate plane that handles the control information. So what's beautiful about that for security purposes is if something intercepts the data, it can't really tell the network to do something different with the data from the data plane. The data plane has no connection to the control plane. Only the control plane can control the flow of data. So, is that the future for the general internet? I don't know. There's a lot of questions that have to be answered. Scale, right now, this is happening with 100-something odd research institutions, universities. In 2015, there are 4.9 billion devices on the internet, and in 2020, they're estimating 25 billion devices on the internet. That's a lot harder to manage centrally than 100 or 200 or 300. So who knows? I can't help but think there'll be something different just because the sheer amount of overhead we put into these networks to handle all these things that aren't really necessary. So you need this, and you end up with like a super compute cluster just figuring out and keeping track of all the state of all these devices. A neat implication for this though is stream processing. One of the cool things you can do with this is copy data at the network level. So instead of having to go in, like when you have, say you're doing metrics on the application in your web stack, and you get a request in, rather than having you have your front end varnish or proxy server or whatever handling that request, rather than having to handle it on a server, you can actually have your network equipment split data streams and send it to another server who is just observing a little small part of the data, but it can do that very efficiently without putting processing resources on application servers to splitting that data out for the other servers. Really interesting. High bandwidth, it can do this at whatever line switch speeds are. So if it's gigabit network, if it's 10 gig network, if it's 100 gig network, you can do this. Here's something really cool that we did with this. I'm going to unmute Kyle. So I don't know if that's my speaker. So I'm gonna mute my mic as well. And mute. So what wasn't clear there is we were actually pushing full 4K video from USC all the way to Chattanooga. It says HD in that video. I don't know why. So these students were actually seeing the objectives of a microscope at 4K. It was incredible. It blew me away. I've looked through microscopes before. I'd never seen anything like this. I mean, it was just gorgeous. It was literally a red cinema camera, something that was like used in Lord of the Rings, but pointed at microbiology and on a 55-inch screen. And so that's the kind of thing that this allows. And what the beauty of it was not just that it was presenting this data to the students, but the students were in control of the microscope. So the microscope was a fly-by-wire microscope. It had you could change the objectives, you could move the stage up and down, around, all that from a computer screen. And so the kids had full control, and the latency of that was about 30 milliseconds due to this advanced network. So they were actually able to do it. It was like the microscope was sitting next to them. But that microscope is, with that camera, is a couple $100,000 thing, and you can't put one of those in every school. But with this technology, you can extend the education reach of that to any school, is the idea. And I'm not taking credit for that project. I was involved in arranging and setting up the network, but there were a ton of people who you saw mentioned in the video who made that happen. So thank you. Any questions?
With that, so that network can mitigate DDoS attacks entirely because it's routed by one thing. You pick your destination. There's no, you can't do NTP application attacks because the server knows exactly where it's going to send these packets. You can't just be like blindly, hey, I want these and happen to send it here.
That's right. So yeah, with the central system, you have, when you authenticate with it, you have only authorization on whatever ports you control. So you can only send traffic to ports you control.
Who owns the central system? Yes and no?
So right now it's NSF and actually and we're talking, so there's two things. There's Genie, which has its own central system, and then Internet 2, which is kind of the first commercial level application of this. So Genie is controlled by NSF, and Raytheon actually holds the management contract on that. Internet 2 is actually operated by Global NOC at Indiana University, so it's ran by a university.
So in that protocol, is there any data encapsulation, or is it just raw data on the wire?
You can do what you want. You're given a layer 2 standard Ethernet link between 2 points, and it's up to you what level of encapsulation you want to put on that. If you don't want to put any, the network doesn't care.
Yeah.
If you want encapsulation, go for it. It depends on what you're doing with the data on either end. If you need to address a private network on the other side, that's fine. If you can build your application infrastructure to handle just the raw data coming in and know how to handle it. That's right. Or UDP, yeah.
You were talking about the virtualization of like an IPv4 over this network, right? So that's how we would try to make it coexist.
Right. So all that means when they virtualize on this is that almost everywhere there was a node on the Internet 2 network, there is an IPv4 router. But instead of that being plugged, those IPv4 routers being plugged directly into ports going across those links, they're plugged into virtual ports that get provisioned across those links.
I had another question about the streams. I mean, obviously central management controls all of it. But if I've started a stream and realized for some reason that where it's going is the wrong place, that's just to log in and cancel that stream, or does,
I mean, you can quit sending data from your end.
Well, obviously. Yeah.
But yeah, the central system is what controls all of the nodes. So if you caught it in time, which doesn't seem very likely, you could divert it. But yeah, you would divert it midstream probably.
Can you do that ad hoc? Like, it's incoming, oh, we've had an issue, and we see it reoccurring, we want to start copying the packets.
Yeah, so if anybody's familiar with intrusion detection systems, IPS, IDS, Bro, which is kind of a suite of tools that includes Snort, can actually do that. You can give it control of a switch that is smart enough to do these sorts of things, and when it detects instead of taking all of your data and putting it through an IPS, when it detects certain things in the firewall that look suspicious, it can divert just that traffic to your IPS IDS system. So it can make your ability to manage huge pipes much cheaper rather than trying to run them through the entire pipe. So like Oak Ridge has 400 gigabits of linkage. And when they went to build the IDS, IPS for that, it was really expensive. And it was custom implementation by Snort to handle spreading all the traffic across that many server nodes to actually handle the IDS. And so it's a lot better if you can just have a switch there that can handle that throughput and copy out the data that you're interested in.
So you said that different places in Chattanooga are connected through EPP to the, what is that like? Can anyone like technically, like what's the process like for an individual to like be part of that?
That relationship's really managed by US Ignite because they're kind of the community outreach organization that's funded by NSF. Right now, currently, we have a connection at the STEM school, at the public library, and in the near future, we'll have one at the Innovation Center. And those are currently 1 gig links. So, but if you had an application that sounded like it was part of this or was partnering with it, then we would be able to do that. Right now, we're working on one with the library where they're working with a library in Burlington, Vermont, which is not research-oriented at all, but it's really just the application of this type of technology for non-research projects. And that's research enough. Anybody else?
So it designates the amount of bandwidth that you can have with that pipe. It doesn't have if it says no.
That's right.
Is there any type of queuing, like saying after this person's done with their line, you can have some, or that'd be akin to Comcast oversubscribing everybody and then everybody hits it at once? It's like, nope, can't. I'm just leave it alone. How does that work?
It depends on how it's implemented. For AL2S, I think you can queue it up, but I don't think you can. I'm not sure you can like say, okay, well, give me 10 gigs now, and I'll take 50 when you have it. I think you just have to wait for the 50 to become available. But even though that's really kind of a commercial level availability network, it's still pretty experimental, the control system. But you should check out Global Knock. They're the guys that write the control system, and it's open source. So it's pretty interesting stuff. Good? Thank you.